All right, this video is going to be a little shorter. It's a smaller chunk of the next video, which is how to graph a line, how to write the equation of a line. Huge topic. So we're just going to look at slope really quick. Okay, slope is really a measure of steepness, or you could even think of it as a rate of change. Okay, so in other words, how fast is this thing changing? So if you have a graph, right, if it's not changing at all, the y value over time, right, whatever the y value is measuring, like number of times something happens, amount of money in your bank account, you know, how good or bad your company is doing, something like that. But over time, if there's no change, right, you're not adding or subtracting anything, then the slope would be zero, it's flat. And then we can talk about positive or negative, right? Is it increasing? Is it decreasing? And so that's what the slope is quantifying. It's not just a description. It's actually numerically monitoring this, okay? It also is another way of thinking about just in 2D space, what direction we're traveling in, right? Like if we're a spaceship in a 2D video game, what direction are we traveling in, right? That would be another way to use the slope, okay? So it's a way to think about direction, or measure of steepness, or just how fast is something changing as you move from left to right on the x-axis. Okay, so we have a really easy way to think about it. It's just rise over run. Okay, change in y over change in x. There's a lot of reasons behind that, but it's semi-arbitrary why we chose it to be y over x. But really it's because the independent variable versus dependent variable. We want to monitor the independent on top. But we'll look at now putting that into a formula and actually doing that on problems, okay? So in the real world, we see this. Like literally, you'll see the slope on signs, right? If this has a 12% grade for this hill, that's useful for truck drivers to know how much to brake. Do they need to stop before they go down? Should they keep a low speed? Should they downshift? Because if their brakes get overheated, right, on a hot day going down a big hill, whoo, runaway truck, that's bad news. So a 12% grade literally means, right, 12%, percent means per 100. So 12% is literally equal to 12 over 100. And grade is telling you that's the slope of the line. So in other words, this hill goes up 12 for every 100. So it goes up whatever, 12 meters for every 100 meters. It goes up 12 feet for every feet, or 100 feet that you travel. So because the units cancel, whatever units were on the top, and on the bottom cancel, this is just a pure ratio. So it's saying the ratio of those two sides, regardless of unit, is we rise 12 units for every 100 units you travel horizontally forward. And that tells you how steep this is, right? And we could even, when we get to trigonometry, calculate that angle. And so that would be the angle of depression. But truck drivers are able to identify that quickly on a sign and go, ooh, 12% is a pretty steep hill. Maybe 3 or 4, 6%, not so bad, but yeah, when you start getting up to double digits, it is surprising how much speed you can gain. Okay, companies use this to monitor their, stock prices, predicting how much customers will desire at certain months, right? Are we going up? Should we buy more? Should we, that sort of thing. And also just overall, it is literally the measure of change, right? It is saying, how fast did someone get from A to B? Well, let's look at the slope. Oh, they traveled 8 meters sideways for every 8 meters up for every 1 second sideways. So they went 8 meters per second. That speed is a rate of change. That's what the slope is. Okay, so how to find the slope? You really got two direct options, right? One, if you have the picture, or even if you're given the 2 points and you have graph paper handy, you could just put the 2 points on a graph and count, right? Just make sure that you keep the positive or negative, right? So it doesn't matter which point you start at. So let's say we start at this point, and I don't have a graph here, this is just an example. But let's say to get to the other point, in terms of just horizontal and vertical, we go down 3. So that's a negative 3. And then we go right, on a graph. This is always positive, negative, and this is positive, negative. So right 5 would be positive 5. And then rise over run, we always put the vertical one, the y change, on top. So we get negative 3 over positive 5, or in other words, a negative out front. Doesn't matter where the negative is, 3 over 5. Right, well, let's say we went the opposite order, right? Or let's even say we went the same order, but sideways first. We go sideways, positive 5, down negative 3, we get the same thing, negative 3 over positive 5. Okay, but let's say we even went the reverse order, and we went the top path there. So if we start with this as the first point, we could go up 3. What the heck? That's different. Positive 3, negative 3. But if we continue along this journey from that point to the other, now we're going negative 5. And so rise over run would be positive 3 rise over run negative 5. That's still a 1 negative sign 3/5. So it's still a negative slope. And the reason it's a negative slope is from left to right, we are going downhill. Okay, and I'll talk more about that in a little bit. And then on the next one, we're doing a positive slope. So from left to right, we're going uphill. Okay, and we just count. We go, oh, I went up positive 8, and then I went right positive 2. So the rise over run would be the positive 8 over positive 2 or 4. If I went the other direction, I'll do it in a different color here. Let's do it in green. Oh, no, there's a lot of green already. Let's do it in blue. So if we go down, oh my gosh, it's a negative 8. We went down 8, right? It's obviously the same numbers over here. But we go down negative 8, and then we go backwards negative 2. And so here we would get the rise of negative 8 over the run of negative 2. That still comes out to be the same slope of 4. So it doesn't matter which point you start at and which point you go to. You will still get that same slope. A positive slope means from left to right, it's going uphill. We're adding positive numbers. And then the negative slope means from left to right, we're adding negative numbers, so we're going downhill. Okay? So here's an example. Let's find the slopes of these two lines. So I'm going to count from left to right on both of them. So this goes down negative 2 and right positive 4. So the slope of this line is, well, I'm going to write it off the graph. So the slope of, and you can write M is always the letter we use for slope, and then you can use a lowercase little l to say this is the slope of line L, or you could just literally write slope of L, right? Doesn't matter how you write it. Okay, and then rise over run, so we always put the vertical one on top. So the vertical one was negative 2, and the horizontal one positive 4, and then we just simplify it. So there's one negative sign, so I'll put that out front. Then we reduce 2 over 4 to be 1/2. Okay, let's do the other one now. So I'm going to go from left to right. So we go positive 2, and then positive 3. Again, we're counting unit spaces here. We're not counting like intersections, right? From here to here is 1 unit, not I hit 2 points is 2. So we're saying 1, 2, 3 is how you count on a graph. Okay, so now we're going to write the slope of line, oh, a little cursive M, that's a little ambiguous. So the slope of M is equal to rise over run, so positive 2 over run of positive 3, or in other words, positive 2/3. All right, but the other option, especially if you're dealing with like decimals or fractions or clunky, you don't ever want to be on a graph like counting units with partial weird things. That's when you fall back on a calculator, or you fall back on, just plugging it into a formula and getting an exact answer. Okay, so what this is saying is, literally, what's the change in y and what's the change in x? Okay, notice that they started with the second point and then they subtracted the first point. That's all they're doing, is they're saying, okay, if we start with this and subtract this, right, what we're going to get is positive 2. And then if we start with this and subtract the x value, we get a positive 3. So as long as you keep the order the same, it'll work out. The common mistake is people accidentally, when they plug it in, they end up swapping the values on the bottom. And that just makes your answer off by a negative sign. And so you can always go back to your picture or draw a quick picture and be like, oh, it's supposed to be a positive slope. It's going uphill. I made a mistake. Let me double check my work. Okay, so the slope between 2 points, I'm doing an example here. I rewrote the formula for you in case you're not familiar with the formula. All right, so over here, what I did is I just named these points, right? So this first point is obviously an xy, and this second point's an xy, but we can't have two things named x and two things named y, so we give them a subscript. Again, subscripts don't have any mathematical reasoning. All they are is a name. So I'm saying this is the first x, and then over here, this is the second x. And then there's the first y and the second y. So I'm just naming the points. Okay, so let's plug them into our formula here. So we get the first x goes here. The first y goes here. The second x goes here. and the second y goes here. So we just plug it in. Whoa, talking and writing at the same time. So we plug it in. Notice that I'm using parentheses, and the reason I do that is so I don't mess up negatives. The other common mistake is people just don't take care of negatives and they minus y1. Here it didn't matter on top, right? You have -6 minus 2. But on bottom, you have minus x1, and x1 was negative. So minus and negative should come out to be positive, but too often if people don't use parentheses, they go 2 minus, oh yeah, it's a -2, the negative's already there. My brain's just working quicker than my hand, and they leave it like that. But since it's minus in parentheses -2, it's actually 2 plus 2 here. Okay, and so what you get is -6, go 2 more down, that's -8, and then over 4, so that's a slope of -2. And you could just quickly double check, like just quick hand, be like, how did I get from 2 to -6? Oh, I went down 2 to 0, and down 6 more, so I went down 8, okay? And then how did I get from this x value to this x value? I went from -2 up to 2, and, or up to 0, then up to 2. So I went up 4. Okay, so +4. So the slope should have been -2. So you could just quick do it yourself. How much did the y change over how much did the x change? Or you have this formula to fall back on. Okay, but I just want to then point out that you should always check whether your answer at the end is reasonable, right? Whether you're double checking, doing the math in a different way, you should at least know whether your line's going up or down. Okay, and a tricky thing is like, well, if I do this, you're like, well, if I go this way, it's an uphill, right? But if I go this direction, it's a downhill. Which way is it? Every line's uphill and downhill. I mean, unless it's horizontal. The key is everything's from left to right, right? In our society, we're a left to right society. That's the arbitrary kind of way to describe it. But the real reason is what's happening is when you say you have a slope of like 1/4, okay? Let's say the slope is 1/4. What's really happening, and this is cool, right? What's really happening on your line is you're saying every time on my graph, it doesn't have to start at 0, but let's just pretend it does. Every time you go over 1, you're going up a quarter. Let's say that's at 0.25, right? So you're going up 0.25. So the slope is literally saying how much I add every time I go over 1, right? So if I'm adding 0.5, that means when I go to 2, I'm now at, or I mean, if I was adding 0.25, now I'm at 0.5. When I go to 3, I'm up at 0.75. And when I get to 4, I'm up at 1, right? So what that looks like, right, is we can use this, right? Now, really, the slope is 0.25. It's just every time you go a step over to the positive right, when you add 1 to x, then you are adding that increment to the y value. But look at it. Because we have this denominator, we go, well, if we do a step of 1/4 times 4 steps, aka if we go over 4, these cancel and we go up this much. So that's the reason the fraction ends up being this rise over run on the graph. That's not literally necessarily what's happening. It's just saying every step go up a quarter. But if you go up a quarter 4 times, you've now gone up 1. So that's how we get this rise of 1 over this run of 4, right? And even for a negative number, right, or a 0, right, if I'm just going to erase that really quick, if I have a slope of 0, what that literally means is I start here, I go over 1, add nothing. Over 1, add nothing to the y value I'm talking about. Over 1, add nothing to the y. Over 1, add nothing. So that's a horizontal line. Or what if we had a negative, right? So let's do another one. Let's say I've got this graph, okay? And let's say I have a negative 1/3, okay? So whatever point you're starting at, let's say I start at a height of 1. Okay, when I go over 1, I now add a negative 1/3 or a minus 0.33 repeating. I'm just going to round it, right? So you go down. So now you're at 0.66. And then you go over to 2. You add another negative 0.33. You're at 0.33. And then you go over a third, and now you're at 0. And so what ends up, it looks like, is you went down 1 for every 3 you went over. But really, you're just adding the negative 1/3 every step. So that's what's really happening. So all of this is left to right, saying, if the number is positive, as you go from left to right, you are adding a positive number, so you are stepping up every step of the way because you're adding a positive to the y. Negative slope, as you go left to right, you are adding a negative, so you keep going downhill. 0, as you step to the right, you're adding nothing, so it stays flat. And then the undefined slope actually isn't even a function mathematically. It's like a special case of a straight line. Really, you should just go back to algebra and look at the idea of a function. What a function is saying, like, I don't care what the function does, but if I ask you, like, hey, if I plug in 5, what's coming out of your machine? And you go 3. Then if I plug in 5 again, you better not be lying to me. Like, a 3 better come out. You told me that's what was going to come out. And so as long as I plug in 5 every time and a 3 comes out, I don't care what the function does. You're just not lying to me, right? You're not ambiguous, right? Whereas if I say, oh, I plug in 5 and out comes 3, and then I go, let me just double check, and I plug in 5 and out comes 6, I'll be like, you liar, you are a worthless function, right? You told me something was true, and then it wasn't true. And so that's why in undefined slope here, when I can have a 5 comma 3, so I plugged in 5 and got 3, and then here I plugged in 5 and got 6, that's why vertical line, not only do I plug in 5 once and get 3 and then 5 again and get 6, I can actually plug in 5 and get every single real number that exists in this vertical line. That is the most unambiguous, or I mean, the most ambiguous function ever, or non-function, it's relationship. So that's why this is a special case. And so it won't even have a y equals mx plus b equation next video. So we'll look at that. But really, another way to look at it is the slope of this line is the rise, any number, let's say 5, over a run of 0. So the slope of this line is a number over 0, and you can't divide by 0. So it explodes, right? But there's lots of reasons for that. The main reason is it's just not even a function, so we don't use that in math. Okay, so now let's look at two separate lines. What if we got the slope of our line, and then we say we have another line. Are they parallel? Or they are parallel, find the slope. However we use that, parallel lines are going in the same direction. And remember, slope is the direction of a line in 2D space. So parallel lines must have the same slope. Okay, the slopes are the same. Now, the harder one to remember is perpendicular lines. Okay, we can use math vocab and say, okay, perpendicular lines have opposite reciprocal slopes. So in other words, that means you switch, let me switch the color here. So you switch the positive negative sign, and you switch the fraction to be upside down. So if we started with, I already spoiled the surprise. If we start with, I don't know, let's do a couple. So if we start with original slope is 2/3, then the perpendicular slope is, my pen is too thick here. Let's go way thinner. Then my perpendicular slope is you switch the sign, so it's now negative, and then you flip the fraction, so it's 3/2. Right? So you take the fraction originally, you flip it over and switch the sign. If it was negative, it becomes positive. So if we start with a 2, we go, that's not a fraction, it's impossible. We just say, well, it's 2/1. I mean, if you want to write any integer as a fraction, you just put it over 1. And so we flip it over, so we get a 1/2. And then again, it was positive, so this would be negative, would be the perpendicular slope. Another way to think about it is that the two slopes multiply to make -1. Okay, so if you think about it, right, like let's take 2/3 and it's perpendicular, which is flip it over a negative, we get negative 3/2. Well, always the flipped over fraction is going to perfectly cancel with the other fraction to make 1, and we switch the sign. So if the first one was positive, then the second one's the opposite, so they always multiply and make -1. So that's a quick way to check two slopes to see if they're perpendicular. Actually, cool is that works in more dimensions than just 2. It's called the dot product, and it's between vectors, and it's really cool. And that's actually a way you will use, or a way that is used in linear algebra to actually calculate the angle between two lines in any dimension space, right? It doesn't have to be 2 or 3. It could be like in 5 dimensions or something. And you might be like, what's 5 dimensions? And in computer science, it doesn't really matter, right? Literally, 5 dimensions is a number, comma, number, comma, number, comma, right? The numbers could stand for anything. It doesn't have to be like a location in space. It could just be like a list of values. That's 5 dimensions. And then just finding differences and stuff and analyzing it in really cool ways. Okay, so if we start with a negative 5/4 over to the right here, well, then we'd switch the negative to a positive, and we'd flip the 5/4 into 4/5. So we could do tons of examples, but we're going to stop there with the examples because I'll do homework problems after. The question is why, though? Why is it flipped over a negative? Like, I mean, is that just some arbitrary thing that a math wizard told us? Okay, no. Here's the reason, okay? Think about like you're programming a little robot. You got a little robot here, okay? Okay, robot, what should I do? And we go, okay, well, robot, I want you to start out pointing north, okay? And I want you to take I want you to take 5 steps forward. Okay, so we're going to walk 5 steps. And so if we were, what we do is we'd be like, okay, start north. Okay, then we go 2, 5 steps. Okay, so we went 5 steps. Tick, 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 tick. Got it. And then we go, okay, now right turn. Okay, 90 degrees. Got it. And then step 4 is 2 steps. Okay, so we do a little 90-degree turn, click, and then we go 2 steps. And that's our slope right now. That's our little robot's got it. Well, if we want to go exactly 90 degrees difference than that, all we have to do is do the exact same steps, right? Except we start 90 degrees in a different direction. So if you think about it, right? If the robot goes 5 steps and 2 steps aside, that's some diagonal direction. Well, just imagine you take the robot and you swing it 90 degrees. That original direction is just 90 degrees swung from the original. So let's look at it. So if we swing this, what we get now is the robot is pointing either direction. It doesn't matter. Let's do both, right? So if it's pointing this way, it takes 5 steps this way, right turn 90 degrees, and then 2 steps this way. Or let's say we started it pointed west. So now we just literally rotate this start north 90 degrees. So if we're pointing west then, we just go 5 steps. We take a right turn 90 degrees and 2. And so what are those 2 slopes? Well, both slopes are down -2, right +5. So that slope is -2/5. Or this one over here, let's say we go the opposite direction in terms of counting. So we go up +5, left, I said +5, up +2, left -5. So that slope is +2/-5. Or in other words, -2/5, right? So we flipped the 5/2 over and we switched the sign. So it's really a rotating 90 degrees in 2D space. That's what the end result is. You just rotate that same 5-2 path 90 degrees, and that's what's switching the sign and then switching the order. It's really cool. Okay, anyways, let's just do a bunch of examples now, okay? So Curtis and Lori are asked to calculate the slope between these 2 points. So you could just put those on a piece of graph paper and count, right? Or you could plug them into your formula. So I'm going to label these. Okay, it looks like both of them used, they started with this one as 2. So I'm going to go, this is xy2. And then this is xy1. Okay, so they did x2 minus x1. Oh, y is on top. y2 minus y1. And x2 minus x1. So let's just check. So y2, oh yeah, that's, no. I thought we caught it. Okay. Oh yeah, look at that common mistake. So look at this. So here, 4 minus -13. 4 minus -13, correct. Over here they did 4 minus +13. They plugged in the wrong value here because 2 negatives should have made a positive, and they messed that up. Same thing for the bottom. It should have been 15 minus -6, and that should end up being positive, but they just went, whatever, there's some negatives there. So make sure to take care, okay? So Lori made that mistake that I said was a common mistake. Okay, open-ended. Give an example of a line whose slope is 0, and then an example of a line whose slope is undefined. So a slope is 0. If you just want to do 0, what's 0 as a fraction? I don't know, 0 is 0/5. So let's just graph it. Here's a graph. Start at any point, and then go up 0, and go right 5. There you go. That's a slope of 0. A slope of 0 is a horizontal line. So this is horizontal. And then you kind of have to remember the one for undefined. Or you could just remember the fact that the only number that's undefined is when you try and divide something by 0, or so far. Then you could, and then algebra 2 is square roots and negatives. Or is it undefined? No, we can give it a value and explore. And when we get to calculus, we can get what's when you get close to dividing by 0. But it's really when you divide by 0. That's when slope is undefined. It's a vertical line. And on a graph, you just start at any point, and you go a rise of 5 and a run of 0. So that's a vertical line. Okay, so those are the 2 cases where you have this undefined slope. Or you have a slope of 0. Slope of 0 is totally normal. We use that one all the time. Undefined slope we don't use all that often because mathematically it doesn't work out. There is an equation for that line, but it's kind of a special case. Okay, determine the slope of the line that contains these points. All right, so let's do it. So I'm going to call this xy1, and this is xy2. Okay, so slope is change in y's, rise, over run is the change in x's. So we start with y2, -1, minus y1 is 3. And then on bottom, x2, -2, minus x1 is -4. And then we just distribute the negatives. We get -1, -3. And then down here we get -2 plus 4. So up top, -4. On bottom, +2. And we get a slope of -2. All right, and let's look at this one. So we already did this one up above. We're going to redo it, okay? So it says find the slope of each line. So we just count this really quick. So -2, 1, 2, 3, +4. So the slope of this line is -2 over +4, or whoa, I can't write it diagonally like that. Let's do it right here. Slope is -1/2. All right, for the bottom one, we'll say we rise 2, we run +3, and so the slope of this line is +2/3. All right, so then it says find the slope of any line perpendicular. Well, what the heck? They didn't they didn't draw this line. We can't count it. How am I supposed to figure this out? Well, remember how to find perpendicular slope. Well, we have the slope of L, and so any line perpendicular, we don't know what point it passes through because the line could be anywhere perpendicular to this. We don't have a point to give it a location, but we absolutely know its direction. Its direction is that opposite reciprocal. So we know that the slope of L is equal to -1/2. So then the perpendicular slope is, we flip it over, so we get a 2/1. We switch the negative to be a positive, and +2/1 is just the same as 2. Okay? Now, what about graph the lines that satisfy each equation? And I put a graph in here. Slope of 2 contains 1, 2. So slope of 2, remember, that's a 2/1. So I'm going to start at the point 1, 2. That's this point. Oh, I'm going to change colors here. Okay, so we're going to start at 1, 2. And then we're going to go slope of 2, which is up 2/1. So up 2/1, up 2/1, up 2/1, up 2/1. I do a bunch of them. And then 2/1 is the same as, so positive divided by positive results in a +2, but also a negative divided by a negative would result in a +2. So we could also go down to -1, down 1 to -1, down to -1, and so on and so forth. You could do as many as you want. So what I'm going to do then is I'm going to start at the top point, and I'm going to go whee with my super straight line like that. And then we just put a big fat arrowhead on both sides. Here we go. And then we'll do the second one. Contains that and is perpendicular to, oh, good golly. Okay, so we have a point, right? I'm going to do this in, I don't know, let's do, no, purple's too close. Let's do orange. So it contains this point. So we start at 6, 4, okay? So we know it goes through this point. And then it's perpendicular to this line. So what we're going to do is we're going to find the slope of MN. Okay, and once we find the slope of MN, then we can flip it over and change the sign. Okay, so let's do x1, y1, x2, y2. So y2 minus y1 is 2 minus 0. And on bottom, x2 minus x1 is 1 minus 5. There were no negatives, so that's why I didn't use parentheses this time. Okay, so 2 over -4, so that's a -1/2. So if the slope of that line is the -1/2, then the perpendicular slope is equal to flip 1/2 over, and we get 2/1, and change negative to be positive, we get positive 2/1. So, oh my gosh, look at that, exactly the same slope. That's freaking crazy. You might even say that these two lines are parallel to one another. And so again, I'm just going to do my super straight line there, and then I'll add an arrowhead to the end and an arrowhead to the end. Perfect. Okay, find the slopes of each line. So there's a bunch of different ones here. So from A to B is down 3 and over +1. So this is -3 over +1 or -3. Okay, I'll erase that. PQ. So from P to Q, I always kind of tend to go left to right. So P to Q, I'm not going to just guess and say, well, it's 2 and 1, because that might not be hitting that point exactly. It definitely doesn't look like it hits that point. The only points I know are these dots. So I'm going to count all the way to the dots. It might work out that there were shorter steps, like maybe it passed through points, but I don't know that. So I'm going to start here and go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that's plus 9. And then 1, 2, 3, 4, 5. Oh yeah, there were no steps in between that worked out nicely. I actually cannot count. I know I'm a math teacher and I can't count. So I'm going to double check that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I'm pretty sure I got the 5. 1, 2, 3, 4, 5. Okay. So that one was positive 9 over 5. And then LM. Okay, let's erase all this. So LM, from L to M. So I'm going to go from M to L. So we'll go, let's go from L to M, whatever. So down 1, 2, 3, 4, 5, 6. That's negative 6. Back, negative 1. So I get a slope of negative 6 over negative 1, or positive 6. Just to double check, is that a positive slope? Yeah, from left to right, we are going uphill. So that is good. Okay. And then let's do one more, just counting the others. We'll have to actually do some parallel perpendicular stuff. So from E to F, we're going up 0. So I already know the slope, but let's do it anyways. 1, 2, 3, 4, 5, 6. So the slope will be rise of 0 over run of 6, or a slope of 0. That's totally right. Yes, we get slope of 0 for that. And then it says a line parallel to LM. Well, we already did the work on LM. So LM has a slope of 6. So this has the same slope. So the slope is 6. Okay. And then line perpendicular to PQ. Well, we already did PQ. So all we got to do now is flip it over. So it's perpendicular. So we flip over the 9/5 and it becomes 5 over 9. And then we get a positive becoming a negative. So we get a slope of negative 5/9. Okay, perpendicular to EF. Well, we have EF is 0. Okay, so it says find the slope. Well, the slope, if we were to flip over the 0 over 6 from EF, we get it 6 over 0 is the new perpendicular slope. But that's really just, it's undefined. And how could it be undefined? Again, that's because it's a vertical line. That's the special case. It's not even a function. Okay, and 32 is a line parallel to AB. Well, it's just the same slope. So 32 is, the slope is just the same as AB, or negative 3. Okay, determine the, oh, this is a good one. So anytime you have an equation, like for example, A times B equals C. Whoa, that's an arrow. Equals C. Right, of course I could plug in like 2 here and 4 here and go, oh, 2 times 4 equals, and I could get that C is 8. But I could also use that same equation and not plug in A and B, but instead plug in like A is 2 and C is 8. And I could say, well, what times 2 is equal to 8? And I could work backwards. So just because you have an equation that's set up as like there is an output doesn't mean that's the only place you can plug in numbers. You can plug in numbers anywhere in the formula, and as long as there's only one unknown, you can go ahead and solve for it. So for example, let's just use the slope formula, right? So slope formula says slope equals y2 minus y1 over x2 minus x1, or in other words, negative 3/7. So I'm plugging in the slope, which we haven't done in the past, and I'm plugging in the 2 points. So I'm going to call this x1 y1, x2 y2, and so I'm going to plug all those in. So negative 1 minus 2. There was no negative here, but we could still put it in parentheses. All over x2, which is an x, what, a variable, minus, and then x1 is 6. Okay, so this is equal to, well, let's just do it below. So negative 3/7 equals, this is negative 3 over x minus 6. Now, if you're like, what the heck, how am I supposed to do this, okay? Well, one thing is, if the tops of the equations are equal, well, then the bottoms have to be equal. You could just jump to this logically. But let's do it more mathematically. Maybe you just want to cross multiply. So let's cross multiply, remembering that this is a package deal. Because of this horizontal line, it is absolutely implied that everything on bottom is a unit. So when you cross multiply, this is negative 3 times the group x minus 6 equals negative 3 times 7. So we distribute. I'm going to take it up to the top right here now. So we have negative 3x plus 18 equals negative 21. Now we subtract the 18 from both sides. We get negative 3x equals negative 39. We divide by negative 3 on both sides, and we get x equals 13. Let's just double check. If we went right to here, 13 minus 6 is 7. So yeah, we get negative 3 on top and 7 on bottom. That looks to be good, okay? So x is 13. So again, we just used the same equation, but instead of plugging in all 4 of these and getting m, we plugged in 3 of them and the end result and said what was the one missing value. And that's a totally valid way to use an equation. Don't be so rigid that like everything has to be given to you and you can only calculate the output. You should be able to unwind and surgically take apart expressions or equations to work backwards. Okay, so another question just like that. We're going to do it the same way. All right, so I'm going to write the equation. So m equals y2 minus y1 over x2 minus x1. I'm going to call this x1, y1, x2, y2. And so let's plug it in. So we get the slope. Oh, wait. This is good. It doesn't give you a slope. So it's just like the last one, except instead of giving you the slope, they give it that the line containing this is perpendicular to, and so you already have, right, we can plug in all these numbers. So we go, okay, so y2, that's negative 4, no, that's 5. What am I doing? So y2 is 5, minus y1 is 2, all over x2 is negative 4, minus x1 is x, and it's equal to, and we just need to figure out that slope really quick. Well, we could do that. So it's saying that these two lines are perpendicular. So that means whatever the slope here is, we need to flip it over and change the sign, and that's the slope of this line. So let's go ahead and figure it out, okay? So the slope is, and I'm just going to plug it in with the second point as my second, and this is my first. So that's negative 1 is y2 minus y1 all over x2 minus x1. Okay, so now we get on top, that's negative 1 minus 8, or that's negative 9. And on bottom, we get 2 minus 4 is negative 2. And so we get the slope is positive 9 over 2. So that means, since it's perpendicular to our line, that means the slope of this line is negative 2/9. Okay, so now let's go ahead and solve this then, now that we've got an equation here. All right, so we got negative 2/9. And I'm just going to put the negative on top. You can always put the negative on top or bottom. You cannot put it on top, or on both. If you put negative 2 over negative 9, that's a positive. So you can put the negative on top, because negative 2 divided by positive 9, or on bottom, 2 divided by negative 9, or out front, negative as a whole 2/9. But don't put it in both. That's a common mistake. Okay, equals 3 over negative 4 minus x. Okay, so let's cross multiply this. So we get negative 2 times the quantity, negative 4 minus x, equals 9 times 3. So that's positive 8, positive 2x, equals 27. I almost wrote 18. So we subtract the 8 from both sides, and we get 2x equals 19. We get x equals 19 halves. Okay. You could always plug that in too and double check. So the last two we're going to do is just looking at real world scenarios. Okay, and these will be the last two. So estimate the annual rate of change of the median age from 1970 to 2000. Okay, so on the bottom we've got 1950, 60, 70. So we're starting right here. 80, 90, 2000. So we're saying what's the average rate of change from here to here? Okay, so the average rate of change is about from this point to this point. What's the slope? So it tells us 35.3 there. Over here, maybe this was like, I don't know, let's just say it was about 28. Let's just say estimate. So I think the rise over run, right, the average rate of change here for 39, for that 30-year period, is I think it went up about 28. So let's say, yes, 7.3 is what it looks like to me, right? Went up from 28. Just looking over here is 25. Here's 30, and it looks like it's a little over half, just to erase. That's what it looks like. So yeah, it looks like 28 to me. And then over, and then common people would write 3 there. But what are the actual units at the bottom? We're talking about years. So that was over 30 years. So we went up 7.3 years over, so that was age here. So I meant years like in terms of age. And then plus 30 years in time. So we get an average slope of, we could estimate that. We could plug that into a calculator. We get that's around, let me see. It's going to be just under, okay, sorry, I had to pull out my calculator because we're estimating here. So the slope is about 0.243 years of gain for every year of time that passed. Okay, and then if the median age continues to increase at the same rate, what will be the median age in 2010? So what if 10 more years passes? What will be the target age here? Well, what we're going to do is we're say this is how much we gained each year. So we multiply it by 10 and we get an average of 2.43, right? And then we add that to this and we go, okay, well, wait. Yeah, what will be the median age? Well, I was curious if it was going to say how much would it increase or what is the actual result. So for 40, you'd say, well, we have 35.3 in 2000, right? Just to erase this so we could see it. So 10 more years from now, you go plus 10 times the slope because we're going up 0.243 each year on average. And so we get an end result of plus 35.3, using my calculator here, 37.73. All right, and then let's look at the last one. Suppose that after 2000, the median age increases by 1/3 of a year annually. So it's going to speed up a little bit. Instead of about a quarter, or 0.24, it's speeding up to 1/3 of a year annually. In what year will the median age be 40.6? So we're saying if it keeps going up from a value of 35.3, then how many years would it take before it gets up to a value of 40.6? Okay, and that's at 1/3 per year. So let's subtract those two. So we're saying how far would we have to go over to get 40.6 minus 35.3? So we got 5.3 left over there. So we're saying how many years would it take to go up 5.3? Well, if the slope is up 1 over 3, right, we could just literally multiply this by 3, right, because that's the one up, and then you go over 3 of those. So 5.3 times 3 is equal to, it would be 15.9, or around 16 years. Another way to do it is say, okay, well, if we want to go up 5.3 and we're going up 1/3 each year, you would say how many years? And so we'd say, well then, this is 41, we'd say, well then, let's divide 5.3 by that 1/3. See how many 1/3 are in that 5.3. And that's the same thing as multiplying by 3, so we still get the 15.9. So it would be about 16 years, okay? Let's see. For exercise these, refer to the graph. What is the rate of change between 98 and 2000? So here's 98. Here's 2000. And so the rate of change is we went up from 51 to 77. So we're going to go for 44. We're going to go, well, the slope is the second y value of 77 minus the first y value of 51. All over, we went over 2 years. Okay, so that's going to be 26. Yep, over 2, so that's 13. So on average, it's going up about 13% per year. Okay, but I mean, that could be used for any number of years or anything on that graph. Okay, then if the percent of classrooms with internet access increases at the same rate as it did between 99 and 2000, so that's different. Oh no, it looks like it's constant, but let's double check. Okay, so let's do, just to see if it's actually going up by a constant rate. 77 minus 64 all over 1 year. Okay, and that would be 13 over 1. No, it is going up at a steady rate on this graph. As the same rate did between 99 and 2000. In what year will it reach 99%? Well, let's just check. In 1 more year, it would go up 13%. What's 13 plus 77? That's 90%. So it would be up at 90% the very next year at 2001. So that was easy. We didn't even need a calculator or anything for that because it would just literally go up 13 more in 1 more year. Will the graph continue to rise indefinitely? So now we're just saying this isn't an abstract math line that goes on for, there's realities here, right? Well, instructional classrooms with internet access, the maximum you can ever have is 100%, right? This is percent. You can't have more than all of the classrooms with internet. So no, right? 46 is, it would likely approach 100, but I don't even know. Is it ever going to reach 100%? Yes. I mean, everybody's going to have internet, right? We got things going on, plans everywhere. But I mean, you could make a one-room schoolhouse out in a farm in the middle of nowhere with no internet, maybe. Who knows? But it's going to, yeah, it's going to approach 100%, but it can never pass it. So there's an upper limit. So whether it reaches 100 or not, there is a limit to its growth. So it will start to slow down within the next year, because you can't add 13% to 90. It would be 103%. So within the next 2 years at least, it would have to slow down. Good questions. All right, you guys, I hope you enjoyed the video. I'll see you next time for the bigger one on equations of lines.